All right, guys, so what we're looking at in Chapter 4 is exponential function, okay? So an exponential function, what I want you guys to know is that it is simply a function in which the variable is located in the exponent, okay? Now, what I think people struggle with sometimes with working with exponential functions is obviously with the exponents in the, or sort of variables in the exponent, there's going to be times that we're using our laws of exponents and that kind of stuff to manipulate things, and sometimes we're not as comfortable with our laws of exponents as we should be. We'll see maybe a little bit of that today as we're trying to kind of analyze the relationships between certain exponential functions and how we can use laws of exponents to show those relationships. I don't necessarily care for the way that they've written this here as f of x equals a to the x. It is absolutely true, but a lot of times, if that's the way you learn what an exponential function looks like with base a, you sometimes get confused when they do something like this, when they write like 2 times 3 to the x. Okay? A lot of people want to take that and write it as 6 to the x. Can I do that? No, I cannot do that because laws of, so your order of operation says you have to, when you evaluate, you have to do 3 to the x first, right? You have to do exponents before you do multiplication and division. Well, I cannot combine this to 6 to the x. Okay, those would be 2 completely different graphs. So in order to remind ourselves of that, this is what I like to do, is k times a to the x. Okay? Some textbooks you'll see it written as a times b to the x, where b is your base and a is your multiplier. We're just staying consistent with what kind of our PowerPoint here is. We use k times a to the x. Okay? A is your base, and once a changes, we have essentially what we call a new parent function. So 2 to the x, if a is 2, that is a parent function. If a goes to 3, 3 to the x is another parent function. Okay? 4 to the x, 5 to the x, 6 to the x, 7 to the x, they're all new parent functions. However, all those parent functions are kind of like brothers and sisters, okay? Because they act the same way, okay? So that's something to kind of think about as we, and I'll show you some examples here in a moment. We manipulate k and a, we should be able to see maybe that relationship, okay? We want a to be greater than 0. A is going to be greater than 0. The other criteria is that a cannot be 1, okay? If a is 1, it's kind of a boring thing, all right? Think about taking a, and if it's 1, and then raise it to the x. What's a raised to the first? Or what's 1 raised to the first? 1. What's 1 raised to the second? 1. What's 1 raised to the third? 1. So I got the points 1, 1, 2, 1, 3, 1, 4, 1, horizontal line through 1, right? Kind of boring, not showing the same behavior that all other exponential functions show. So that's why we put that restriction that we don't want a to be 1. Okay. So giving you that definition, let's now look at a graph of k times a to the x. So I've got that k value up there on the slider. I got a on the slider. We can change those things and kind of see how that impacts our graph. So I'm going to start with k being 1. So if you didn't even want to put it in there, a lot of times if k is 1, it's just like all our other polynomials. Like I have x squared plus 3x plus 5. A lot of times I don't write 1x squared, right? So if I have that 1 out front, the k is 1, it's kind of understood to be 1. If you don't want to write it, you don't have to. Okay? So I'm just looking at 2 to the x here. Okay? If I write 2 to the x, okay, look over there on my graph. You see when x is 0, that black point? What's 2 to the 0? 1. Okay? 2 to the 0 is 1. So I get 0, 1 as an ordered pair. Okay? Let's start with a different a value. Let's go 3. What's 3 to the 0? 1. Do you see that if I go 4 to the 0, I still get 1? So does it make sense that regardless of what my base is, okay, and even if I go kind of over here between 0 and 1, we'll talk about this in a little bit, but regardless of what my base is, as long as I keep it, so when it's 0, things kind of vanish, right? You see the fact that when it's 1, it's kind of boring, okay? But I always have that point 0, 1 in there, no matter what A is. That's because when I raise anything to the 0 power, I get 1, right? Okay. Now, you see that I have the generic point 0, k there, right? 0, k, because if I have a k out here that is different than 1, let's say my k is 2. You see how I took that 1 and multiplied it by 2 and gave me that vertical stretch of 2? If I take it and let it be 3, you see you took that k value of 1 that I normally have on my parent function and stretch it to 3, okay? So if you want to remember the 3, so this is the idea, these 3 points are on every single parent function, 2dx, 3x, 4dx, okay? But instead of remembering as 1 comma, like 1/2, sorry, 1 comma 2, 0 comma 1, and then -1 comma 1/2 for 2dx, and then saying, okay, well, it's 1 comma 3, 0 comma 1, and -1 comma 1/3 for 3dx. Okay, can I see what I'm doing there? We just remember as 1 comma a, 0 comma k, and then -1 comma 1 over a, and I should be able to get the 3 points in that are always on that curve. Now, I have a little bit of a, say maybe I should do this. Oh, didn't do anything. Okay. All right. And I should probably put maybe a K there. No, I gotta have it there. Because if K does change, then it applies that vertical stretch to those, correct? Okay. Now, for the most part, that vertical stretch is a transformation, okay? So usually when I graph these, I'm not saying you have to do it the way I do it, but if I want like 4 times 2 to the x, I will graph the parent function 2 to the x. So I will use 0, 1. I will use 1 comma 2. I will use -1 comma 1/2, and I'll plot those. And then I'll go back through and multiply all those y values by 4, okay, or whatever my k value is. But if you want to do it all together at one time, those would be the 3 points on any exponential function that is applying just a vertical stretch. Is that all right? Okay, those are very, very, very useful for us. And they're going to allow us to graph every exponential function. Now, in addition to that, later on in this chapter, we're going to deal with logarithms. Okay, exponential functions and logarithmic functions are inverses; they undo each other. Okay, we're going to see a lot of applications for exponentials that are a little bit more interesting, I think, than maybe applications we've used so far for other functions. Okay, if everybody at some point in their lives is going to be influenced by or impacted by finances, right? Whether it be credit card debt, whether it be college loan debt, whether it be a mortgage, okay, car payments, you're going to somehow be impacted by finances in that way, right? Okay, at some point you're probably all going to want to start saving money, putting money away in different accounts, okay, maybe stocks and bonds, maybe you want to put them into annuities and stuff like that, or hedge funds. Those things, in the way that we calculate finances with those, and the dividends that are returned from stocks and bonds and that kind of stuff, uses exponential functions, okay, because of how we understand what interest is, okay? And we'll talk about this a lot more on Monday. But within the finance kind of area or field, exponential functions and logarithmic functions are very, very useful for us to kind of extrapolate future values of principles and that kind of thing. Okay, does that make sense, everybody? So we're going to see examples like that in story problems that deal with finance. There's also going to be maybe you've seen it in science. If you've taken, have you guys talked about Newton's law of cooling in science? So you guys probably understand it. If I were to take, like, say, some hot chocolate out of the microwave, okay? Maybe my hot chocolate is boiling because I just don't know how to make hot chocolate in the microwave. So it's at 212 when I take it out, okay? I put it in a 68-degree room. What is the temperature of that hot chocolate going to eventually become? 68 degrees, right? There's no way it's going to become like 30 degrees, right? Okay? It's going to become the ambient temperature of the room. So Newton's law of cooling states that and shows you how that works, and we can go through and determine, okay, if my ambient temperature is 68 degrees, when I pulled that thing out of the microwave, it was 212, and now it's been 5 minutes, I should be able to tell the temperature of that liquid without putting a thermometer in it using Newton's law of cooling. Does that make sense? Okay. I can also predict then, you know, if I want to, if it's 212 and I think it's palatable to drink at maybe 100 degrees, I can work through Newton's law of cooling, the formula provided, and come up with the exact time that I can take a drink of that liquid, because that will then be 100 degrees. Does that make sense? Anybody like forensic science? So forensic, like CSI type stuff, okay? Like a coroner, so you find a dead body, okay? Coroner comes in and takes a thermometer and sticks it in like the liver of that dead body to check the temperature of it, right? Okay, the liver is like the most like centralized and retains the heat, the core temperature of the body the best. Okay, so they do that. They measure the ambient temperature of the room that person died in, and through Newton's law of cooling, they can get a rough estimate of when that person, how long that person's been deceased. Does that make sense? And now we can start to piece together kind of a case against what happened. But Newton's law of cooling and exponents and exponential functions and logarithms allow us to do that. Okay. Anything on a scale, a lot of times is logarithmic. So the Richter scale, magnitude of earthquakes. That's not what we use anymore. We've got a better scale for measuring earthquakes, but that was logarithmic. pH scale. You guys know what the pH scale is, right? Okay. It is the measurement of hydrogen ion concentration in a substance, and we use the pH scale to give us those numbers of what is it, 14 to 0, is that right? Okay, and 7 being neutral. So those are all scales that use exponential and logarithmic functions. Okay. So why am I saying that stuff? When we learn how to graph these exponential functions, that's great. But at the same time we're learning how to graph these, we're doing it in the hopes that we can use them to graph in logarithmic functions. Because logarithmic functions, you're going to find out, probably one of the hardest things to graph, just with you know, kind of the technique we've used so far to graph other things. Okay. If I wanted to graph them, I could obviously use a t-chart and that kind of stuff, and choose x values, evaluate, get y values. That's a pain in the butt, very tedious. The best way to graph logarithmic functions is to understand that exponentials and logarithms are inverses. So if they give me a logarithmic function and I want to graph it, I'm not going to graph it directly that way. I'm going to work through my inverse procedure and come up with the exponential that is the inverse of that logarithm, graph that exponential. Then once I have those points on my exponential, say I have 1, 2 on my exponential, then don't I have 2, 1 on its inverse, which is a logarithm? That kind of make sense? And we'll talk more about that down the road, but we'll open your eyes to the fact that it is very, very important that we learn how to graph these exponentials, because they will be the direct tool that we use, or the main tool that we use when we graph logarithms. Okay. So just kind of showing you some relationships here that we should kind of be familiar with already. If I start obviously taking that K value and stretching it or shrinking it, okay, it is just impacting the Y's, right? Okay. If I put in, just to maybe see this a little bit better, if I put in the line x equals -1, x equals 0, and x equals 1, okay, put in those 3 vertical lines, just as kind of visual indicators for us, you see that when I change K, don't those points simply shift up and down on those lines? Okay, so that's telling us that we're doing a vertical stretch, right? Okay, so that's nice. Okay, that's the same as any other function, right? If I had x squared and put a 2 out front, a 3 out, 4, 5, 6 out in front of it, it's going to take the y values and stretch them. Smell like something's on fire? Kinda? You guys smell that? Like a burnt up motor or something. All right. We already had our fire drill, so we're good.
Yeah, we're fine. Okay.
Exactly. The K times A to the X, so we got 1. Let's do this. Let's say that I take K to be 2, just real quick to show you the difference here and why this isn't something that we want to do. If I've got 2 times 2 to the X, that's a vertical stretch of 2 to my parent function 2 to the X. I want you guys to understand visually that is not the same thing as 4 to the X, right? 4 to the X is that green curve, not the same as 2 times 2 to the X, right? We have to make sure that we understand that concept. Let me go to a different GeoGebra here to show you the other transformations. And I was just going to, a lot of times, so like 2 to the X, let's just put all these in here. 2 to the X, 3 to the X, 4 to the X, 5 to the X. They all look very similar, right? Obviously, though, the larger the base, the faster the y values increase. Because taking 2 to the third, giving me 8, taking 5 to the third gives me 125 right away, right? Okay, so obviously the larger the base, the quicker that thing increases. I like to use 2 to the X in a lot of my demonstrations. And if we can do the work with 2 to the X, we ought to be able to kind of transfer that over to all the other ones. All right, so if I take 2 to the X, take that red curve, and let's just multiply by a negative out front. What's that do? Flips it. Okay? Just like everything else, right? It's like a parabola. I multiply by a negative out front, the next axis reflection. Okay? What happens if I multiply just the x by a negative? Gives me that, right? Now here's a question. I think this is very important for us to understand. If I have 2 to the negative x, can I rewrite this way? Does this change anything at all? Is that still 2 to the negative x? Rewrite this one over here. Okay. Does this one, now because of my laws of exponents, because we're talking about understanding how our laws of exponents work, when I have a fraction raised to an exponent, laws of exponents tells me it's this, isn't it? Like that? Okay. Well, doesn't that mean if I've got negative exponents, does it? Or isn't the way that I get rid of negative exponents, I take that base and that exponent and I transfer it to the other side of the division bar? So if the numerator becomes the denominator, the denominator becomes the numerator. So can I take this 1 to the negative x and make it 1 to the x in the numerator? Okay, and now can I take this 2 to the negative x and make it 2 to the x in the denominator? Okay, so now I'm going to reverse, because these are the same exponents, I'm going to reverse the thing that we did here. Here we distributed that x to both parts, right? Or use kind of a distributive property, but to pull it back out. And I get that. What's it tell me? 2 to the negative x is exactly the same thing as 1/2 to the x. Graph, so I got 2 to the negative x, I got 1/2 to the x. Give me a thin curve. Okay. So that's, I think, a very important thing to understand. And I didn't show you that here, but when we change our a value, obviously when our a value is 1, it's kind of boring. Kick k back to 1. But a is between 0 and 1. Okay, do you see how it changes? The function becomes now always decreasing. Okay. When a is bigger than 1, it's always increasing, right? we call these graphs or these functions that are always increasing or always decreasing, we call them monotonic, okay? Because monotone means the same thing, right? Doing the same behavior over and over again forever. So a graph that is always increasing, always decreasing, a lot of times we call it strictly monotonic. So we've got that idea, that's great. What if I take and add 3 to the end of this thing? What did it do? Moved it up 3, okay? So adding or subtracting to the end of the function is like always, moves it up or down, right? The one thing that people struggle with is seeing what happens. How do I get it to move left or right? I add to the x, right? So this is the way you're going to see it written, because the x is in the exponent, so you're going to see that x plus 3 written in the exponent. Does that make sense? Okay. So now I see it that plus 3, so it actually moves it left 3 units, right? Okay. Think about this. We're talking about this, but let's say that I just go back to 2 to the x. If I have, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, as that exponent getting bigger and bigger, all my y values getting bigger and bigger. Okay. If I go 2 to the negative 1, well, that becomes 1/2, right? If I go 2 to the negative 2, that becomes 1/4. 2 to the negative 3rd, 1/8. 2 to the negative 4th, 1/16, right? Okay. Is there any way that I'm going to get rid of that 1? It's always going to be 1, right? So will this number ever become 0? No, it's never going to be equal to 0. We'll get really, really close to it. Is 1/16 closer to 0 than 1/8 is? Mm-hmm. Is 1/32 closer than 1/16? Okay. So when x is, say x is 10, okay, is 1 over 2 to 10 getting closer to 0? But it never gets to 0, right? So y equals 0 is a what for us? An asymptote, okay? Every exponential is going to have one of those, okay? Now, if I add, like I said, if I add 3 to this, so we went plus 3. Now, where's my asymptote? Yes, y equals 3 is now my asymptote. So every time that you do a vertical shift, your asymptote moves with that vertical shift. Is this okay? So what needs to be understood, I think, is that all the transformations that we've done so far this year, they are consistent for all the functions that we're doing, okay? And every function that we'll ever come across, the transformations all apply the same way. Now, where you add to x might be in a different position. It might look different. Does that make sense? But we got to understand our order of operations. Are we adding to x before we apply the exponential function? Okay, before we take 2 and raise it to something, we're adding, that 1, we're adding 3 to x before we did that, okay? So it'll look different for logarithms. Adding the x will be a different spot for logarithms. It'll be in a different spot for trigonometric functions later on, okay? But if we can understand adding to the entire function moves up and down, adding to x moves left and right, multiplied out front by a multiplier is going to be a vertical stretch, that kind of stuff, okay? Yes? Do you still follow the HSID? Yep. We can still do, and this is another one of those functions that we can still have horizontal compressions and stuff like that and horizontal stretches. We can do this. Oh. Okay, so you can see that exponent can be 2x, okay? And you can see how that compares then to 2 to the x, okay? Take the green one, put your hands on the right-hand side of the green one, left-hand side of the green one, and put your hands together. It's going to squeeze down and give you that red one, right? Okay, but it also looks like it might be a vertical stretch. That is a horizontal compression, but it also looks like a vertical stretch. And that's the problem with, again, exponential functions and evaluating or looking at those relationships. So a lot of times we don't talk about the horizontal aspect of it. Have you guys heard of the natural number? Maybe I don't know if in science you guys call it Napier's constant, that number right there. Yeah. That number, I believe, if we I don't think I can do it on GeoGebra. I'm going off memory. I could be wrong. I believe it's 1 plus 1 over x, that quantity raised to the x power. As x gets really, 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 really big, that quantity turns into this number. Okay? It's E because of Leonard Euler. Okay? Mathematician who was working with it. Sometimes called Napier's constant because he was also another guy that was working with it at the same time. But that number becomes very useful for us. You guys talk about the natural logarithm, right? Ln. Okay? What happens is that there are particular bases of our exponentials and our logarithms that we like to use that kind of occur naturally in like finances or just in the environment, that 2.71828 number is very, very, very beneficial to us. Okay, so what I want you to understand though is that when I write, so a lot of times we'll be graphing like e to the x. Okay, well e guys is just a number very close to 3, right? So that's e to the x. There's 3 to the x. Okay, they're very similar, right? It's just taking another number. It could be rational or irrational, raised to a power, and you get that curve. All right. Have a great weekend.